Welcome to The Explainer. Today, we're going to tackle something that can feel, well, invisible, electricity. But we're going to make it visible. We're going to break down complex DC power systems using a super simple analogy, something you already get: water flowing through a pipe.
I know, right? A glass of water explaining your phone's battery? It sounds a little out there, but trust me on this one. By the end of this, you're going to see exactly how the physics of a simple water pipe can totally demystify something as complex as a battery system.
All right, so here's our roadmap. We're going to start with that basic water analogy, then we'll build up our terms step by step, and we'll wrap it all up by figuring out exactly what a real-world power system can actually do.
All right, let's dive right in. I want you to completely forget about wires, circuits, all that stuff for a minute. Just picture this: water flowing through a set of pipes. That's it.
And this right here, this is the core idea, the absolute key to unlocking everything else we're going to talk about today. This idea that electrical current acts just like water is the foundation for everything. So keep that mental picture of flowing water in your head as we start to dig in.
Okay, so now it's time to start mapping the technical lingo of electricity onto our water analogy. This is where those abstract terms you've heard, like volts and amps, are going to become something you can actually visualize.
First up, volts. So what are volts? Simple. Think of them as the water pressure in your pipes. You know, when you turn on a hose, that's the push behind the water. So a 12-volt system has a certain amount of pressure. A higher voltage system, well, that just means more pressure, giving you a way more powerful spray coming out of that hose.
Next up, we've got amps. If volts are the pressure, amps are the flow rate. It's the sheer volume of water moving through the pipe. So, think about it. A really wide pipe can carry way more gallons of water per minute than a skinny one, right? Well, a system with more amps has a greater volume, a bigger flow of electricity.
Okay, and this is where it all comes together. Watts. Watts are the total power of the system. It's the actual work that can be done. And you get it by multiplying the pressure, that's our volts, by the flow rate, which is our amps. In our water world, this is the real deal power, like how much force you have to spin a big water wheel.
And this just lays it all out side by side. It's so simple when you see it like this. Voltage is your pressure. Amps are your flow rate. And watts, that's the total power you get when you put them together. Pressure times flow equals power. It's really that straightforward.
Okay, so we get how the power flows, but where does it come from in the first place? Well, every system needs a place to store its energy, and that brings us to the battery. Or, for our analogy, let's call it the power tank.
This brings in a new term, amp hours, or AH. And it's super simple. This is just the size of your water tank. That's it. It tells you the total capacity, how much energy, or water, your battery can hold. So a 600 amp hour battery, it's literally like having a 600-gallon water tank ready to go.
Now, the system we're going to use for our example today is a pretty beefy one. It's built on a battery bank that has a total capacity of 600 amp hours, and it operates at a pressure of 12 volts. These two numbers, the capacity, our tank size, and the pressure, our voltage, they're the keys to everything that follows.
And here's where the magic really happens. When we combine those numbers, when we multiply our 600 amp hour tank size by the 12-volt pressure, we get our total energy storage. That's 7,200 watt-hours. Now that number represents the total amount of energy we have to play with. It's the total volume of work we can get done.
All right, we've got our storage tank and it's full of energy. Awesome. But how do we get that power out in a way that our everyday stuff, our coffee makers and laptops, can actually use? Well, that's where the inverter comes in.
So the inverter, think of it as a really sophisticated smart pump or a converter. You see, batteries provide this steady, one-way flow of power called DC, or direct current. But all our home appliances, they're built for the alternating current, AC, that comes from a standard wall outlet. The inverter's job is to do that crucial conversion from DC to AC.
Now, the inverter in our system is rated for 3,000 watts, and this number is so important. In our water analogy, this is the size of the tap. It's the absolute widest that tap can open. This defines the maximum amount of power you can pull out at any single moment. You could have a swimming pool-sized tank, but if you've only got a tiny little tap, you can't run a fire hose. You can't run more appliances than this tap can handle at once. So when you look at it this way, the whole path of energy is actually really simple. First, you've got the energy stored in the tank. That's our 600 amp hour battery. Then it flows through the pump, our 3,000 watt inverter that converts it. And finally, it gets used by the sprinkler or, whatever appliance you've got plugged in.
And this is the moment we've been building up to. We're going to take everything we've just learned, put our water analogy to the test, and answer the biggest question of all.
So, let's lay it out. We have a 7,200 watt-hour tank and a tap that can open up to 3,000 watts. The big question is, what can we actually power with this thing? Let's look at some common household items and see how our system stacks up.
Okay, check this out. The numbers here really tell the whole story. You want to run a power-hungry coffee maker? No problem. It draws 1,200 watts, which is way below our 3,000 watt limit. Our tank could keep that thing brewing for about 6 hours straight. What about a big TV? That's only 150 watts. You could run that for 2 full days. And a little laptop charger? A mind-blowing 120 hours. The only rule, the only thing you have to remember, is that the total power of everything you're running at the same time has to stay under that 3,000 watt tap limit.
And this, right here, is the key takeaway. If you remember one thing, let it be this. Understanding any power system is just about balancing two things, your tank size and your tap size. The tank size, that's your battery's amp hours, tells you how long you can run your stuff. And the tap size, your inverter's watts, tells you how much stuff you can run all at once.
And there you have it, the whole system totally demystified. The next time you look at a battery or a spec sheet, you're not going to see a bunch of confusing numbers. You're going to see a tank of water, a pump, and a flow of energy. So now that you can translate watts and volts into pressure and flow, what are you going to build with it?